Episode 91, Baby Universe. And welcome back for another edition of the Syzygy podcast. Emily, sitting opposite me at the table here in her office. There's two things. Number one, we're in your office, which is nice. We haven't done that terribly much. But number two, it's been a while.
Yeah, I didn't actually look up to see how long it's been, but...
Probably best not to.
Yeah.
Look,
embarrassingly long.
Listeners, we know. We don't want to labour the point, but we know it's been a while. And look, bunch of stuff's been happening. There's been Christmas. That was a while ago. There was a fairly significant COVID peak here in the UK, and that kind of took over for a while. Emily, have you had COVID?
No. I'm one of the rare ones, I think.
You must be the one left
I'm missing
that
out.
hasn't. Yeah. I got it literally over Christmas. I got it, I think, on the 22nd of December, having been really careful. We're going to have Christmas, no COVID. Oh, no, we've all got COVID. So we had Christmas in lockdown with COVID, like many other people, but we came out of it pretty well with just, some flu symptoms and the like. So we're all fine in that regard, but that's kind of happened. And then, Emily, you got really busy with work. Work's been going kind of nuts, which is really cool.
Yeah. We're all back face-to-face teaching at the university, which is brilliant, and I love it, and I hated that we had to do it any other way. Mm-hmm. But it does make things rather busy.
Yes, you do have a certain look on your face, which is a look in your eyes, which is kind of, it's all happening, and it's all happening at once. And so, Emily and I have been trying to get together to record this episode of this podcast for a while now, and it just kept happening. I got sick, I had a cold, and then I had another cold, and Emily got busy. Doesn't matter. Point is, we're here now, finally back for another episode of Syzygy. So thank you to everyone out there in listener land who's been sticking with us all this time, waiting for us to make an episode. And in particular, I'd like to give a shout out, thank you to all of our supporters, our financial supporters through Patreon, who just continue to support the show. We've just had a website rollover on the show, which means your support keeps those electrons flowing. So that's really, really cool. Thank you, everyone, for sticking with us. On with the show. Except before we get to today's topic, there's a couple of things that we probably need to have a bit of a chat about. First of all, Emily, I'm old now.
Yeah. You aged a little. So.
I did. I mean, I know everyone out there listening to this might sort of, in your mind's eye, I don't know how you picture me. It's probably as a strapping sort of mid-20s hipster kind of guy. I'm not that. I'm really not. I turned 50 just before Christmas, just before I got COVID, in fact. I don't know if the two things are related. And I'm, kind of feeling it. I feel 50.
It's just a number in a strange counting system that doesn't make any sense.
It's
Chris.
True. It's just 50 laps around the sun, really, isn't it?
Except it's still not even quite that, because you've got to count all the leap seconds, etc., of the Earth's orbit.
Hang on, does that make me older or younger?
Does it?
Look, I'm going to use that. I think Emily, the astronomer, has just informed me that I'm actually not 50 yet, and I'm going to go with that. But just before we started recording, Emily said, I might actually have something for you. Have you?
Well, I got you a present because you're going to have a party.
Yeah.
And then you didn't.
And then I didn't. I was going to have a big 50th birthday party, and then COVID happened, and the idea of getting a bunch of people together suddenly seemed really, really bad. So we didn't do that.
And it's now March, and I feel like I could just hang on to this and give it to your 51st, but maybe it doesn't quite feel the same.
Look, let's just get this over and done with. I'm 50 now.
Well, open your present then.
Oh, it's here, hiding here behind my screen. Hang on. It's a box.
You might have to turn it upside down.
The medium of audio podcasts doesn't really lend itself. Ooh, it's okay. It's got written on the top, "The Milky Way in a Sphere." Hang on a sec. Feels a little bit Harry Potter at the moment because I'm getting something orb-shaped out of a black velvet-lined box. Oh, wow! I was about to say check that out, but you can't see it. I will put a picture up. This will be the chapter art in the show notes. That is gorgeous. We have a crystalline sphere. Glass sphere with the Milky Way galaxy in it.
Yeah.
Like all of it.
The real one.
Wow. That's beautiful. Thank you so much.
Real data.
Based on real, so that's not just artist impression.
Oh no. This is proper science.
Wow. In the sense of what? Like where the locations of all the stars and things are?
Yep. And there's even the large and small Magellanic Clouds.
Oh, there are too. Look at that. They look like little smudges in the glass, but it's not those. That's so cool. Fantastic. That is going straight to the pool room. Do you know that reference?
No, but I'm very worried if you're going to play billiards with it.
No, that's not what I meant. If you haven't seen it yet, the Australian film The Castle, definitely worth a watch. Straight to the pool room. Oh, that's very exciting. I like that a lot. Thank you so much. Now, that's not the only bit of personal behind-the-scenes syzygy news, me turning 50, but there is something which actually does influence the podcast quite significantly in terms of personal news. Emily, what's been going on with you recently?
Yeah, well, over Christmas, so, you were just lying in bed feeling a bit sorry for yourself having COVID.
Yeah.
Turns out I was getting fatter.
Oh, like Christmas largesse, was it? Lots of turkey and booze, was that?
Turns out it wasn't actually anything to do with Christmas.
Oh.
So it turns out that I'm now pregnant.
Hey!
Yeah.
I mean, I did know this. I'm sounding very excited, but clearly, obviously, sitting here in front of me, I know, right? But you out there in listener land don't necessarily know this. That's exciting.
Very exciting.
Wow. A whole brand new astronomer going to be launched into the world. Launched makes it sound like a very active process. Sorry about that.
If only it was that easy.
Yeah, well, although I don't know, that does sound kind of a little bit painful. Anyway, that's exciting. So, like, roughly when?
Yeah, so towards the end of April,
right,
we're welcoming our first baby into our little family.
Wow. That's very, very cool. So that may have an impact on all sorts of things, from, your day-to-day life, amount of sleep, entire patterns of operation during the day. But it also might have a small impact on what we do here on the podcast. And so in celebration of that, we thought, well, why don't we do a little series of appropriately themed episodes? And so we're going to start today with one of those. Emily, what are we talking about today that is completely and utterly appropriate to your current condition?
Well, I guess as most people who have gone through a third trimester will know, basically your brain gets taken over by all sorts of weird hormones going a little bit crazy all the time.
Yeah, so I've heard. I mean, I haven't been there myself, but I've witnessed it twice. And, oh boy, yeah, fun times.
So I'm going to go with I've got baby brain at the moment.
Okay.
Or baby on the brain.
Mm-hmm.
So why not just translate that straight across into astronomy and talk about baby things in astronomy?
Sounds good to me. So where do we start? What kind of baby things do you get in astronomy?
Well, you could get all sorts of baby things. We've talked, or at least alluded to, baby stars, baby planets, baby galaxies, baby clusters, all sorts of things, stellar nurseries. There's actually a lot of, I guess, language that astronomers use that is relevant to a life cycle. We talk about the life cycle of stars. And someone tried to tell me off about that once because it would confuse small children that they think that stars were actually alive. And I thought, no.
Whoever that person was, I don't think has ever actually observed a child. Kids use language and analogy all the time to make sense of the world. Why not the universe?
Well, and this is what we use as professionals. Like stellar nurseries is not just something we decided to call these places because it's cutesy. It's actually a descriptive word that makes sense, that's translatable across languages, and it works, and we use it professionally. We
intuitively understand what that means, and in a universe which is full of creation and destruction, why wouldn't you talk about that in terms of life and death? And I think if you anthropomorphize things too much, you run the risk of, I don't know, putting in stuff that doesn't exist. But I don't think talking about the birth and death of stars is making them seem too lifelike. I think that's okay. So let's go with this. We're going to talk about baby things over the next however many weeks until exciting things happen.
Until suddenly we just stop.
That could be sooner. It could be later. We'll see. But today we were going to start with, well, Emily, what? Where are we starting this baby journey through the universe?
Well, I think you got to go all the way back to the very beginning, right?
Right.
So I thought we would start with talking about baby universe.
Are we talking about as in when it was first there, like the very early epochs? What are we talking about?
Yeah, so I think broadly we talk about the very early universe or the primordial universe as being something like up to the first 100 million years.
100 million years. Now that, this is one of those things, right? We often come to in this podcast. 100 million years sounds like a really, really, really long time. On the other hand, how long has it been since the Big Bang? Current estimates, 13.78, something like billion years, which is a lot of millions. And so the first 100 million, did you say?
Yeah.
That's a while, but
And
it's
to
not
be
a lot.
fair, I think we're really actually going to talk about mostly the first 10 seconds.
Right, because that's where all the action really happened. Okay, so that's what we're talking about today, is the universe in its infancy. Cute little baby universe. You can imagine it as Baby Yoda, but in universe form. I think that sounds good to me.
And it's kind of the key milestones that the universe goes through in its growth and development. Yes, I'm going to have a lot of analogies.
There's going to be a lot of this over the coming weeks and months, folks, so strap in. Okay, so where do we start?
Well, I've got a good quote. It's my favourite quote to talk about, and I use it in my lectures, and I talk to my students. It's just the best when you start talking about the kind of birth of the universe. So I'll read it to you now. In the beginning, the universe was created. This has made a lot of people very angry and been widely regarded as a bad move.
There's Douglas Adams, right? Hitchhiker's Guide to the Galaxy?
Yeah, Restaurant at the End of the Universe, to be
very
precise.
Nice. Yeah. Can I pick up from that? The universe was created. I mean, if we're going to go with this birth analogy, one of the questions that often comes up, particularly from kids, is, where do babies come from? So can we just throw that one out there, put it on the table? Emily, where'd the universe come from?
Well, this is going to be, there's two ways you can go down the road to answering this. And I'll start with one way, and then I think we're going to spend most of the time in the podcast on how we're going to answer this, the second way, which is kind of the sciencey. We're going to talk about the Big Bang and what that means and so on and so on. But there's actually kind of a very philosophical thing when you can say the universe began at the point that time t equals 0, let's say, right? Why the universe began and exactly how the universe began and what happened before it are all complete unknowns to science.
Or indeed what that question even means. Like how can you even talk about before if that's where time started?
Yeah, exactly.
If space and time are one and the same, it's all part of, the four-dimensional space-time of Einsteinian stuff. Like if it began then, that's what time equals 0 means, then what does before even mean? These are big questions.
Yeah, and that's why I'm saying they're more in the philosophical realm.
Yeah,
now,
and science just goes, yeah, good question. Anyway, moving on.
Yeah, and in some ways science doesn't care. Anything that happened before the Big Bang is irrelevant to the science that we use in the universe around us today. Doesn't matter. So you can either take that approach and think, we're just going to put that over there, it's somebody else's problem. Or indeed you can leave that open to interpretation about your own creation faith if you want to. So there's a lot of space in there to build in whatever you want to believe about what was maybe before there was a universe, if there was a before, how it happened, who did it, perhaps, etc., etc.
Yeah, I mean, there's an interesting angle on that from the point of view of theoretical physics, people and cosmology, people who are looking at, like, can we find the equation? Put everything together and all of the particle physics and all of the general relativity, all of that together into the big ultimate question that describes, or equation that describes everything, the theory that describes everything. And maybe in that, the universe is inevitable. These are the sorts of things that you hear physicists and cosmologists talking about, that the mathematics will lead the way. But, I mean, it's all, when it comes down to it, there's so much philosophy and personal sort of belief in the centrality of sort of symmetry and beauty and all of that. It all really comes down to, look, just follow whatever your personal beliefs and faith requires you to follow, because when we don't have enough to guide us at that point.
Yeah.
So all we can say is it happened, then what?
Yeah, well, basically there's just one finite point where the universe began in terms of the scientific understanding of the universe. And if you want to think about things before then, that's up to you. But this science goes from this particular point. And this particular point, actually, I've sort of said it's kind of t equals 0. It's actually not quite, actually.
It's almost t equals 0?
T
equals almost 0.
But it's not exactly t equals 0. So maybe we should start from actually saying what we think the whole concept is of the Big Bang, and then we'll come back to this.
Okay, that sounds good. Because a Big Bang is easily said, but
yes.
It's doing a lot of heavy lifting there. There's a lot going on in a Big Bang. So
yeah, well, even the name itself was supposed to be a derogatory term, wasn't it?
Yeah, it was. Who came up with that? Who was that?
Oh, I have to look up the
It
name.
wasn't Zwicky, was it?
It was basically a criticism of the very earliest ideas. And
Like you think the universe came from some kind of big bang, and everyone went, "That's a great, like write that down. That's a cracker." And ever since, that's what it's been.
So basically, the Big Bang is a description of how the universe began, and from a physics and science point of view. We have good evidence for the Big Bang. I think that's important to note at this point. We have really solid evidence around us that we can draw on and say, yeah, this thing happened.
Like what sort of thing? I mean, why don't we start there, at least, is like, how do we know?
Well, there's two very fundamental pieces of evidence, and then there's a few supplementary ones. I think if we just talk about the two fundamental ones, because they're enough on their own to actually
we could be here
you.
for a very long time.
Yeah. So the first one, I think, is Hubble's law. And this is an interesting sort of history that goes behind Hubble's law, because Hubble was an astronomer working in the 1920s, 1930s. He was looking at galaxies. He did all sorts of things. And, of course, Hubble Space Telescope is named after some of the work he did, although it's very important that we recognise it wasn't just him. He was a little bit of a kind of figurehead, and in some ways a chauvinistic one, who had a lot of other people supporting the research that he did, including women and other people.
Yeah.
And important to mention on International Women's Day.
I was about to say, like, this is a really good day to just mention that sometimes the head bloke gets all the attention.
Yeah.
And actually there's a lot of people, and particularly a lot of women, who are doing all the work in the background. So this is one of those.
It's his named after him, but yeah, loads of people contributed to this body of work. And so he was looking at galaxies, and he was measuring the velocities of galaxies and their distances. And what he noticed is that galaxies that are further away from us are moving away from us faster.
Right. And, okay, importantly to remember, like, it's around about this time that we actually learnt that there are even galaxies.
Yeah, exactly.
So, hey, there are galaxies other than ours. Like, we're in one, and there are these other ones, and the ones further away are moving away from us faster than the ones closer. Like, it's not just random motion. They should be all going in different directions, but they're moving away, and it's faster the further away you go. What does that mean?
Well, does it mean that we smell really, really bad?
Like, everyone's running away from us, Emily. This is not good.
No, this is an observational effect, and it's nothing to do with the fact that we are in some kind of preferred location in the universe. You could be on any galaxy that you want in the universe, and you will observe exactly the same thing. And what's going on is actually that the universe is expanding, is the bottom line here. So further away that you are, the more space there is in between us and that galaxy. Space is the thing that's expanding, so the more space, more expansion, moving faster.
Right. I mean, the analogy that you often see is, imagine you're a bit of dried fruit inside a fruit cake or something that's cooking in the oven, and as the cake's expanding as it's cooking, every bit of raisin or currant or something in there, we'll see all of the other bits moving away from it because the cake itself is expanding. Well, the cake is space, and we're on a little bit of raisin in the universe, and we see all the other raisins moving away from us because of that expansion. But it's not that we're the center of the cake and everything's moving away from us. Everyone else, all the other raisins, would see exactly the same thing.
Yeah.
Yeah.
So it's a big thing to get your head around, and there's loads of implications, and we'll have to spend another 4 or 5 episodes about what the other implications of this. But the critical one for today is that if things are expanding and moving away from each other, then in the past they were closer.
Play that movie backwards, and everything comes towards each other. And that was the basic calculation, wasn't it? It was, well, hang on. We could actually just directly work out how long ago we were all piled on top of each other.
Yeah, because all you need to do is measure the rate of that expansion, and then you turn it upside down, and then suddenly you have when was everything in the same place.
Yeah, taking a movie of the cake baking, you run it backwards, and when does that all go back into the gloop that you put in the oven in the first place? And what was the number that they came up with, first of all?
It was about 13.5, 13.6 billion years.
Oh, so, right, from the very beginning.
Yeah, so it was really...
Wow.
Well, it depends on what value, how good your measurement was of the Hubble constant, we call it, the acceleration rate. And if you take the sort of, we're not great at measuring this value exactly, but we can get it ballpark. And if you just turn it upside down, then that's exactly where you end up.
Yeah. Okay. So that, you said there were a couple of main sort of fundamental bits of evidence. One of them is everything's rushing away from us. And the further away you are, the faster it's going. Wind that tape backwards and you get everything clumped together. And so there must have been a Big Bang that pushed everything apart. And that's where that came from,
Yep.
right? That was the idea. Initially, as you said, people sort of poo-pooing the idea, saying, what are you saying, that the universe just exploded in some kind of Big Bangs? Yeah, that's exactly what we're saying.
Yeah, and in some ways I think we take that thought for granted now. We know that the universe evolves and changed and has a finite lifetime, whereas, 100 years ago, everyone just assumed that the universe has just been here forever. It's always going to be here.
Yeah. It was one of the fundamental assumptions was, well, the universe is clearly static. Like nothing on the broad side, scale of the universe, nothing's really changing. So that's important. We hang on to that one. So no, very much not that.
Yeah, massive paradigm shift there.
Yeah.
And the second piece of really strong evidence for the Big Bang is something called cosmic microwave background.
Right.
Which I think we've talked about a few times. We
think
did actually
we
have a whole episode on it.
Yeah.
Really good. So if you want to, find out all the deep, dark, dirty secrets of the cosmic microwave background.
There will be a link in the show notes to the exact episode.
Yeah. But the summary is that we have this background of radiation that runs through the entire universe that's at very, very sort of low frequency or microwaves, actually, as in the name.
Hence the name, yeah.
Yep. Which indicates that there was basically a single time in the universe where photons suddenly became free to move around the universe. And since that point, they've sort of expanded with the universe and cooled down and become these microwave photons.
Yeah. Now, this is kind of subtle. And again, we went through it in detail in that episode. But if I remember correctly, the idea was that back when the universe was really young, it was really hot because everything was squeezed together, right? Really, really hot, which meant that you couldn't have like atoms. You could have all the bits of atoms, the electrons and protons and a few neutrons and so on. But they were all like, they weren't joined together to make atoms. They weren't bound together. And so you got a lot of charges, electric charges, racing around at really high energy. And any electromagnetic radiation, any light, would see those charges and sort of bounce off them. And so the universe is just this soup of radiation and matter. And then as it cooled, got to the point where the atoms could form. Like the electrons and the protons could sort of stick together to make atoms. And suddenly, like in a really relatively short period of time, the universe went from being this opaque soup where the light's bouncing around to being effectively transparent because all those charges kind of went away because the positives and negatives joined together. And so the universe is basically then neutral and the light could just pass through. And the cosmic microwave background, if I've got this right, is what's left over from that moment, that when all the light went off through the universe, and it's been sort of slowly cooling down ever since. But we can still see it.
Yeah.
Which is amazing.
And the incredible thing is it's exactly the same no matter where you look in the sky. So it's not that it comes from a particular direction and you can say, hey, the Big Bang happened over there, because that wouldn't work anyway.
Right. Yeah.
It's everywhere because the Big Bang happened everywhere and the whole universe just released these photons everywhere in the universe
I mean, there
at the
are
same time.
tiny little changes that can tell you an enormous amount about sort of the structure of the universe. But the fundamental idea is to, within a small correction, it is the same everywhere. And it's not just, hey, that there's this radiation and it's the same everywhere, but it is exactly the temperature that you would expect it to be if the universe has been expanding for 13.8 or whatever it is, billion years.
Yeah.
Like, it's a really, really amazing piece of data. It's beautiful.
Yeah, you couldn't have wished. It's one of the most amazing, I think, matches between observational data and the theory that predicted its existence. It's just one of those moments where you're like, excellent, case closed, close the textbook, we've done it.
And what else could this have been? Like, it just fits the Big Bang model so well that it's like, nope, we've done that one. We're pretty happy with this idea. So we've got the galaxies rushing away from us, the Hubble law thing, right? Yep. We've got the cosmic microwave background and all of this put together, plus, as you said, a number of other really good pieces of evidence that we won't go into today.
No.
Says Big Bang happened.
Yep.
Fantastic. All right. Where do we go from here? Should we talk about the very, very infant universe?
Yeah. Now we're going to talk about the very early universe. And in the very early universe, we're going to talk about 4 different forces. And I think it's really important to just let you know what those are to sort of up front, so that when we start sort of pulling them out, then it kind of makes a bit more sense.
Might get a bit jargony, you reckon?
Possibly, but we'll try and
reel it in. Yeah.
So in the universe around us today, we have 4 fundamental forces. Come on.
All right, okay.
Here's
Well,
your name.
gravity.
Yes.
Gravity's a big one. And on the scale of the universe, like that is the big one. That's the thing that keeps everything together.
And also the weakest one, interesting.
Well, yeah, it is. But that's mainly because all the others are acting at such close range that they clump everything together, right? So you've got gravity, and then you've got electromagnetism, which is positive and negative charges, right? Which stick together to make atoms.
Yep.
And that's chemistry. That's all of chemistry, everything. And in fact, it's basically almost everything that we see and experience around us. It's light, it's chemistry, it's atoms, it's everything, right? And then there are two nuclear forces, which we very rarely see. One is the weak nuclear force, which is actually, you can combine that together with electromagnetism to make one unified theory called electroweak, but that's a story for another time, and we probably already got a podcast on that anyway. But that's about certain fairly rare interactions between particles, things like neutrinos and certain nuclear decays.
Yeah.
Right? And so that's the weak nuclear force. And then there's the strong nuclear force, which ultimately is responsible for sticking the nucleus of the atom together. The protons and neutrons inside the nucleus, like protons, positive charge, shouldn't stick together. They should repel. But there's a stronger force. What do we call that? I don't know. The strong force. And they stick the protons and the neutrons together to make the nucleus. So that's the four. Gravity, electromagnetism, weak and strong.
Yeah.
Right.
So we see four in the universe around us today.
Yep.
Brilliant. There used to only be one, we think, force.
That would have been simpler.
Yeah. And during the very early evolution of the universe, that one fundamental force, whatever you want to call it, split into these four ones at different times. And we'll go through a bit when these different changes happen because they're really important. But basically, we go from 1 to 4, and that's the evolutionary history of force in the universe.
Yeah. Do we know that? Like, how do we...
Well, to be fair, we know that it goes down to 2. We know that we can build, so we know that the 3 of them did originate from the single force. Well, we sort of know that.
We think we know that.
Yeah. Whether the 4th one was ever actually part of that is, I guess you could say, up for debate. It's probably one of the biggest theoretical physics challenges
it's tricky.
in existence.
I mean, the whole sort of bringing together of forces is a really quite an old idea. With electricity and magnetism, we never thought were the same thing. And then it turns out, no, it isn't the same. Just different sides of the same coin. It's electromagnetism. And then we were able to combine together, theoretically, the weak nuclear force and electromagnetism. And it's two different sides of the same thing. We just see them playing out in different ways in the world. And so that gives us a lot of confidence in physics that maybe we can keep going with that. The strong nuclear force, we haven't yet found a way to do that, but there's a lot of ideas going around, and string theory is in there, and
what's called grand unification theory, isn't it? Yeah. Which sounds very impressive, doesn't it?
But really hard. That's been the promise for best part of 40 or maybe 50 years now, is we can do this. We've done it with all these others. Surely we just crowbar this one. No, it's really, really hard. And then there's gravity, and gravity is different.
It operates in such a fundamentally different way to all the rest of the forces that I think, I say that we can go back to 1. Maybe that's more of a philosophical idea because we want it to.
We want it to be true.
Because we're human and we like the idea of simplicity.
And also everything that we've seen for the last 150 years of physics has been in that direction, right? Electricity and magnetism and the weak nuclear force. It's all saying the universe operates this way and it's getting simpler. We're combining disparate ideas together into, no, that's the one thing. We can write down one equation that describes all of this stuff. Just keep that process going and we'll get there. It might not happen.
Might not.
But it might.
Yeah. So whilst we have some reasonable ideas, I would say, well, some of them are reasonable.
Some of them are
that we might be able to combine
crazy.
into the grand unification theory. 3 of the forces, the 4th one, I don't think no one has any clue.
No, but people are working on it. Quantum gravity and all sorts of things. It's hard. It's hard in ways that we can't even begin to describe, but it's hard.
But let's spin the dial around the other way and actually go from sort of 0 to when these forces started to appear in the universe.
So let's take as read that we had a force, a super force. Yep.
And this was at the time which we call the singularity. Now, singularity is a mathematical concept that mathematicians love. physicists hate and astronomers just kind of ignore. That's my summary anyway.
Yeah. Nice one. What's the problem with it? Why do the mathematicians love it but the physicists hate it?
Mathematicians like working with constructs like infinity. So a singularity is infinite stuff. Like, so for a black hole, it's infinite density in a black hole. And actually for the universe and the Big Bang, we're talking about infinite density again in a single point. So infinite stuff in zero space. Dividing by zero is not really a thing you're supposed to do, but
you often hear people talking about, scientists talking about, the laws of physics break down inside black holes and stuff. And that's what they're saying, is that, you can calculate using the equations that we know from Einstein and others, what gravity does to mass and energy, how it all fits together in the vicinity of a black hole. When the mass density gets so much that not even light, nothing can escape. Great, okay, that's fine. That all sorts out nicely in the mathematics. But what's actually happening down inside there is still an absolute mystery, because the math says, well, it'll just keep collapsing down until it reaches a singularity, that you get an infinitely dense point. And math stops working at that point. As you said, you start dividing by zeros all over the place. We can't deal with it. We don't know what that means. So there's lots of theories around, well, maybe that doesn't happen. Maybe the physics does change or break or something before that point and something else kicks in. But we don't know. We have no idea. And that's just a black hole.
Yeah.
Try winding it back to the beginning of the universe. We have no idea. But yeah, it's complex.
Yeah. So physicists don't really like the idea that their physics is not working in these situations.
No. And the astronomers just, let's ignore that and move on. Let's move forward in time.
We sort of say, that's a black hole. Cool. Now what effect does that have on its surrounds, and what can we learn
measure?
from it? Yeah, exactly. So, and maybe that's the same here with the singularity. Anyway, so we have this thing, whatever, that's then going to cause the universe to come into existence. Now, I said that there is a time, which is not actually zero time, where physics starts.
Right.
And that time is called the Planck time.
Mm-hmm.
Now, I don't think we've talked a lot about quantum physics.
It sort of enters every once in a while, and I get very excited. But
yeah. So the Planck time is the smallest unit of time that we can possibly ever observe. It's a fundamental limit to what we can actually learn about the universe. And this is one of the concepts in quantum physics that makes people very uncomfortable. Because, so we talk about quantum physics, for example, there is a Planck length, which is the smallest unit of length that we can ever measure. You think we've got microscopes. We've got really great microscopes. We can just look at things that are smaller and smaller and smaller.
Yeah,
and
like
smaller.
we can see atoms. We can see bits of atoms.
Yeah. And we can just build better microscopes if
Surely.
you want to see smaller things, right? Yep. But the uncomfortable thing is there is a fundamental limit to how small you can go, and it's called the Planck length. Because after that, quantum physics takes over and things are probabilistic rather than actually a particle sitting on the table here that we can actually look at.
The whole notion of length just ceases to exist at, in and around the Planck length. That it's so small that it doesn't even make sense. It's not that it's so small. It's the level at which the principles of quantum physics say it doesn't even make sense to think about length. At this distance scale. And the Planck time's kind of similar. That what even is time at this limit?
Yeah.
The good thing is we don't have to worry about it terribly much.
It's a very small number. So the Planck time comes actually from the Planck length. It's the time taken for light to travel a distance of the Planck length. And, the Planck length is small. It is
really small.
It's really small.
Like a lot smaller than an atom.
Yeah. And light travels really fast.
Yeah.
So the Planck time is really small. It's about, I've got 5.4 times 10 to the minus 44 seconds.
Now that's really small. 10 to the minus 44 is lot of zeros after the decimal point, and then some numbers, like huge number of zeros, which means it's a tiny fraction. And normally you could just say, look, surely that's effectively zero. But the difference between effectively zero and actually zero means a lot to people like cosmologists and physicists. Like, it's not zero. It's almost zero, but it's not zero.
And the awkward thing is, it's at the Planck time that we think that the first separation of our forces may have happened, which is the separation of gravity from what is called the electronuclear force.
Right.
So electronuclear contains the strong force, the weak force, and electromagnetism all bundled into one.
Right. And I can sort of maybe intuitively, speaking as someone who has no idea what he's talking about because he's never studied these things, but if the Planck length and the Planck time is basically where quantum physics says, well, maybe you can start thinking about space and time as things, below that you can't, above that you can, then something like general relativity, which is all about space and time, I can see how that would kind of, well, we're here now, we're beyond the Planck length, general relativity takes over, here we are, we exist now. So that makes sense, sure.
And I guess if we're going to go with analogies, maybe that's, I haven't given birth yet before, but I'm told that maybe that's kind of the bit up until then that you just don't remember. That's the bit that's wiped out of existence for you. And then your memory just sort of kicks in at one particular point.
How was your childbirth? Oh, look, I don't remember anything up until this point. Everything after that, clear, vivid memory. But up until that point, got nothing for you. Yeah, okay. Let's go with that. Yeah. We'll talk to you in a couple of months' time to see how that worked out.
Well, hopefully you don't remember the bad bits.
Well,
anyway.
Exactly, yeah.
So that's the Planck time. Now, from then on in, so we're starting in, this is very, very early universe, like we're talking, the tiniest fractions of a second. This is kind of what we call the grand unification era. And we call that the grand unification era because this force, this electronuclear force, is kind of what we're trying to figure out using grand unification theory, as we talked about before. And that carries on for a little while, maybe up until kind of 10 to the minus 36 seconds.
So we've gone from 10 to the minus 44 all the way up to 10 to the minus 36 seconds. Well, it's like, wow, that's a huge amount of time. No, it's not. It's a tiny, tiny amount of time. But again, in terms of physics, it doesn't matter. That's what, 8 orders of magnitude. That's 100 million times, longer, which is a lot.
Yeah.
Okay? So even though it's a tiny fraction of a second, a lot can happen in that time, including entire forces splitting apart from each other.
Yeah, indeed. And maybe that's kind of the first time you get a cuddle with your little baby. First little cuddle. Now, something very exciting happens at 10 to the minus 36 seconds, which has a profound impact on the universe today.
What's that?
Well, the universe then goes through its first growth spurt.
Ooh. I do like this analogy. This is really working. Although if that's happening just after you give your baby its first cuddle, I think you're in for an interesting time.
Well,
but yeah, let's go with this.
Time's relative.
Sure.
Right? Yeah.
So, big growth spurt.
Now, that's really understating it. I mean, the universe goes through the biggest growth spurt that we could possibly even imagine. It's a period called inflation.
And even that doesn't capture it, really, does it?
No, it's really bad. So in this period, first of all, we got the next separation of forces that happens. So the strong force and the electroweak force separate out. And then maybe that triggers inflation. We're not really quite sure what the relationship is there, but at least from that point on, we have inflation where the universe grows by a factor of 10 to the 26.
Which is, again, we're throwing around these big numbers. 10 to the 26 is a stupidly big number. And so even if you start with something really, really small, if you increase that 10 to the 26 times, right? You double it and double it and double it. That's an enormous amount.
It's huge. So
can we put any kind of sizes on this?
Well, we can do it in scale that we're more appreciative of, shall we say. So that means if you took something that was about a nanometer.
Okay. And a nanometer, that's 10 to the minus 9 of a meter. That's a billionth of a meter. To put that in context, that's about 10 atoms across.
Yeah.
Right?
So, or if you tend to take your hair, I think it's like a 100th the width of your hair.
Sure.
Something like that.
Yeah. It's small.
That would expand or inflate to the size of 10 light years.
That's quite big. So going for something which is, to all intents and purposes, a few atoms, a small molecule, to something which is 10 light years, which is a long way.
Yeah, so that's further than the nearest star.
Yeah. Yeah, so inflation then is kind of one of those, it's like Big Bang. What happened in that period of time? Oh, universe inflated. Oh, really? How much? Oh, a lot. quite a lot, actually.
And it's even worse than that. It happened quite quickly.
Yeah.
So it happened somewhere between 10 to the minus 36 seconds and 10 to the minus 33 seconds after the Big Bang.
Like in a factor of 1,000, it's increased in size by billions and billions and billions and billions. That would have been fun. That's a fun ride.
It's an interesting thing. We don't know what caused inflation. We do see evidence of it, and actually the cosmic microwave background is a huge part of the evidence that we see. But actually the whole universe around us is got this kind of hangover from inflation. And the hangover is that the universe actually looks really similar no matter where you look.
Yeah.
So the cosmic microwave background is basically the same in every direction. Galaxies, the structure of the universe is basically the same in every direction. And the only way you can really explain that is if it inflated so quickly that it just didn't have time to form diverse structure, basically.
Is inflation kind of one of those ideas? Like, I know that there are a lot of theorists, and some of them may throw something at me. I don't know. I mean, again, I'm not a cosmologist. I don't know. It's always struck me that inflation is one of those explanations for something where we don't really have a mechanism for it. We really don't understand it. We can like cosmologists like to throw around ideas, but we don't know. But it's explaining something we observe in terms of something really quite bizarre that we think might be true. And the thing that we're explaining is, as you just said, that the universe is really uniform. And we wouldn't expect that. In the very early universe, there should have been, lumpiness. There should have been ultimately really, really small, what we call quantum fluctuations. It should have been a bit more of this over here and a bit less of this over here. And that would have turned into, hey, look, the universe is really clumpy. And it's not. It's really not on grand scales. And so we explain that with, oh, well, the universe must have had this crazy inflation. Does that sort of fit with what you...
I think so, yeah. But it also, we can kind of put it in that epoch as well, because this is, again, the separation of force. So it's kind of suspicious that we think this happened at the same time as a separation of forces that we also don't understand. So it's kind of, here's the box of weird stuff that happened in the early universe. The fact that two things that seem quite distinct are both in that same box.
Seems a bit shady, doesn't it?
Yeah, it doesn't seem coincidental to me. But...
Yeah, so the way physicists and cosmologists approach that is, all right, well, let's see if we can come up with mechanisms and ways that this can happen. But meanwhile, inflation has kind of become like canon, right? It's there. It's something that we pretty sure has happened.
Yeah.
Yeah, which is nuts because, as we mentioned, it was a really big deal. Big growth spurt there.
Indeed, yeah. So, okay, well, now we're starting to enter maybe some stages of the universe that become a little bit more familiar, particularly to a traditional particle physicist, shall we say. So we enter the electroweak epoch. So the electroweak force, the combination of electromagnetism and the weak nuclear force, we kind of understand that reasonably well.
Yeah, we've actually got the equations for it and everything. That's the one we've nailed down back in the 70s. 60s and 70s. So
we're entering the realm of familiarity. Also, this is the era of the Higgs boson coming into existence. So that's quite cool. We know about that boson. We've measured it. We've found it. It's all very exciting.
That's the one that's responsible for what we know as mass.
Yeah.
Yeah.
So we can just carry on sort of going through all that sort of phase, if you like. So maybe if we talked about, I don't know, maybe I'm mixing up my timelines of analogies a little bit here, but if we talked about the separation of the strong and the electroweak forces, maybe like a child's milestone of sitting up, then if we get the next separation we're looking for, which is the final one of the weak force and the electromagnetism, might be them sort of starting to crawl around.
And sort of, find... When a child gets mobile... Right, and this is you'll discover this, Emily. When a child gets mobile, that's where you go from, oh, isn't it cute? Look, the child's beginning to learn how to do stuff. To, oh my God, the child's learning to close that door. Quick, look out for the stairs. Like suddenly, it's we've got to actually be really, really careful here. So maybe there's a good analogy there in the universe.
Maybe, yeah. So this sort of this whole epoch lasts until kind of up until about 10 to the minus 12 seconds. And then we sort of start getting some quarks coming in, or quarks, whichever way you like to pronounce that. So, there's a few kind of steps. And we're entering the realm of more and more familiarity to particularly particle physics or anyone who's studied physics.
The universe as we know it is beginning to look a little bit familiar. Yeah.
So quarks are starting to come into existence now, and they are the kind of fundamental building blocks of our fundamental building blocks of atoms.
Yeah. Like if you look inside an atom, you've got the electrons whizzing around the outside, and in the nucleus, you've got the protons and neutrons. But we discovered many decades ago that actually there's another layer inside that inside the protons and neutrons, there are these, as I like to call them, quarks, which, to the best of our knowledge so far, those are the fundamental bits, that they combine together to make the protons and neutrons, and then the protons and neutrons make the nucleus of the atom, and so on.
So that's around about a picosecond and after the Big Bang. This doesn't sound like very long, does it?
No, I mean, we're still talking really, really short periods of time here.
Yeah. But then we go into the Hadron epoch. So this is where the universe is starting to, I keep saying take more shape, take a more familiar thing. But remember, during this whole process, what's happening is the universe started off super, super hot. And as it's expanded, it's cooled. And it's that cooling process that's allowing these new particles to sort of start to form.
Yeah, that's the key. The hotter you get, the more energy you've got crammed into a small space, the more the definition between these different parts disappears. The forces combine together. You can't have, quarks combining together to make protons and neutrons. It's just too energetic. You've just got a soup of stuff. Energetic enough, you don't even have quarks. They're just sort of quickly popping in and out of existence, but you've just got this wash of force. But as it cools, you do get to a point where, hang on, we can do this now. Yeah.
So we're cooling down, and we get to the Hadron epoch, so about a microsecond now. So this is even like normal units of time that we're dealing with
this
now.
Is something sensible now.
Yeah.
And the hadrons are when the quarks combine together, so they can stick together to make, they can either combine together in pairs, so a quark and an antiquark, and that can make something called a meson, or they can combine together in threes to make things like protons and neutrons. And there's a whole bunch of other hadrons which we don't come across in everyday life. But those are the examples that we kind of know about in our world around us, protons, neutrons, things like that.
Yeah. And the most important one, I'd argue, that forms around here is the proton. Because to an astronomer, protons aren't protons. Protons are nuclei of hydrogen.
Right, yes. The simplest element, the simplest atom, hydrogen, is a proton with an electron going around it, orbiting around it. But if you take the electron away, then you've got a hydrogen nucleus, which is just a proton to everyone else. Yeah.
But it's hydrogen to astronomers.
Hydrogen. Yeah. And when the astronomers look at it, they go, no, wait, that's like most of the universe or much of the universe.
Yeah. So the very, very first part of what we now say is, the majority of the elements that we see in the universe.
Right. So that's where that begins, the hadronic period.
So we go to the lepton epoch from there, which is getting up to a second.
Now, leptons are kind of, in particle physics, they're sort of the other side of the coin. You've got the quarks, which can make the hadrons and things, and then you've got the leptons, which are things like electrons, and then electrons have got heavier cousins called muons and tauons. And they're just like electrons, only bigger and heavier, and we don't really know why, but they do exist. But you've also got neutrinos. Every time you make an electron, it all happens through the weak nuclear force, and it's complicated. We'll leave that aside. But every time you do make an electron, you also make a neutrino, which are weird particles, almost no mass, no charge, whizzing off across the universe, huge numbers of them coming from nuclear reactions in the sun right now, passing straight through us, just crazy numbers of these things that we almost never see, but they're there. And so those are leptons, the electron things and the neutrino things.
Yeah. So I guess from an astronomy point of view, first of all, we get excited because there's now electrons.
Yay.
So now we've got the building blocks of atoms.
Yep.
So we've got protons and electrons. They're not atoms yet.
No,
but
we're on the way.
They will become atoms. And neutrinos are actually quite important to astronomy as well. They've kind of, I would say, were they the first multi-messenger kind of particle that we really started looking at in the universe?
How do you mean multi-messenger?
So astronomy's been steeped in history of using photons as the primary way. Like we see light coming from the universe, whether that light's in the optical, X-rays, gamma rays, radio, whatever, it's all light.
Sure.
And that's been the way that we've studied the universe historically, until we started looking at actually what are some other messengers, what are some other information carriers that we could find. And I think neutrinos might be one of the first ones in terms of multi-messenger.
Right. What are the others? What else can you use?
So we've now also got gravitational waves.
Right, of course, yeah, with the colliding black holes and things like that.
Yeah. And we do have a few, it's arguable whether we're getting muons or not, but other particles potentially.
Yeah. Things like cosmic rays. I mean, a lot of that is electromagnetic radiation, but there's also other particles coming out.
Yeah.
Okay.
So in modern astronomy, we don't rely just on photons. It's still the vast majority of the data that we do is photon-based, but there are these other
But neutrinos, really interesting, really hard to spot, but it doesn't mean it's impossible. You can do it.
Yeah, we have massive detectors that we can pick up these things in. Cool. So we get those. Now, then we go to, I guess, where my sort of understanding really starts to kick in. We start to get photons, which are the building blocks of light. So the little carriers of light, they start around sort of 10 seconds after the Big Bang.
Which is, I find that really interesting because we kind of see photons, I imagine light as being just so fundamental. Like it's surely from the absolute, like from t equals 0, surely there was light. But the notion of, well, photons as a thing in the universe traveling across whatever the baby universe looked like at the time only really became a thing after that relatively very long period of time. It's kind of fascinating.
Yeah, no, they're not the first things that come in the universe by a long shot. And also at this time, we've got Big Bang nucleosynthesis, which is, if you imagine the fusion reactions that happen in the sun, you know that we got hydrogen fusing to helium, right?
Yep.
In the sun. There's actually a bunch of other reactions that go on in stars, different synthesis. You can synthesize helium to carbon and all these kind of
all
other
sorts of stuff.
things.
Yeah.
But that's all happening at the nucleus. So the nuclei are sort of interacting with each other and fusing and so on. But that's also happened at the Big Bang. So we get Big Bang nucleosynthesis, which is when we had hydrogen nuclei. We also had helium nuclei, tiny bit of lithium, bit of beryllium. Just the very simple elements were starting to come together at this point.
Right. And again, because like we're starting to make these things, like we've got the protons and neutrons and other stuff all flinging around all over the place with loads of energy. But as we're cooling down, because we're still expanding a lot at this point, cooling down, it gets to the point where, well, they're bashing together because they're so energetic and they're so tightly sort of, squeezed in that there's sufficient energy for them to overcome the fact that they would normally push each other apart, but it's not so energetic that they can't then stick. If it was too hot, they would just bounce off again. But cool down enough, it's like, hey, hang on, these have stuck together now. We've just made a nucleus. Look at that. That's awesome.
Yeah, quite cool, isn't it?
Yeah.
And the electrons at this point are still just swimming around doing their own thing, right?
Yeah, because it's way too energetic to have atoms yet.
This is a plasma, right?
Yeah.
It's just nuclei swimming around in electrons. So, and fundamentally, it doesn't behave that differently to, say, the plasma that's in the interior of the sun.
Yeah, we see that all the time in the universe. Plasma's really common.
But then we get to the build-up. We've been trying to get to this moment, right? The bit where we actually form atoms. So it takes a while for the universe to cool down enough for these atoms to start to form. So we're now going to skip from maybe 10 seconds after the Big Bang when we had this nucleosynthesis. It takes another 380,000 years for the universe to cool enough to make an atom.
Mind you, I mean, look, that sounds like a really long time, but then remember at the very beginning we started at the Planck time, which was 10 to the minus 44, and then we had like 100 million, order of magnitude of 100 million to get to the next epoch. Like, just because the times sound big in our human timescales in terms of years, it's all the same kind of thing. It's just a big jump, right?
Yeah, exactly. Yeah. But then in terms of orders of magnitude, it's probably not so much of a jump as what
not much at all.
We've done in other sections. Yeah.
So what happened then? Atoms formed.
Atoms,
cool enough for
so
atoms
our
to actually
nuclei captured these electrons, which made them into neutral atoms. So you had positive nuclei, negative electrons kicking around, and then you now got a neutral sort of universe.
Which, as we said before, like that's a huge deal, right? Because there's a big difference between a universe filled with charged stuff and a universe filled with charged stuff, but which is now bound together to make neutral things. Basically, unless you're really looking at one of those particles really closely, everything in the universe suddenly becomes electrically neutral. It's not there electrically anymore.
The way I think about it is, you know those really fancy bathroom mirrors where you pass an electric charge, sorry, not mirrors, windows.
Yeah.
And so you pass an electric charge actually through the window and it becomes foggy.
Oh, yeah.
So you can sort of flick a switch and the bathroom mirror becomes frosted.
Yeah.
And that's what the universe was like before recombination or the formation of atoms. But then it's really like flicking the switch and then suddenly everything becomes transparent and
You
clear.
flick the switch the other way and the window is suddenly clear.
Yeah.
And the light can just go wow through the universe. And as we said, that's what we see now with the cosmic microwave background. That leftover radiation was bouncing around. And the crucial part about that, as far as our understanding of the universe is concerned, before that moment, the light bouncing around couldn't really carry terribly much information at all for any distance about what was going on, right? When a photon bounces off, a particle and then bounces somewhere else, it carries a small amount. Oh, I just bounced off a proton. Fantastic. I'm going this way. But then it almost instantly bounces off something else. And we've lost all that. We have no idea what's going on. But when the universe suddenly becomes transparent, all of the light goes off through the universe, carrying information about that moment in time. That's when it went, I'm bouncing around, and now I'm just going to go. And I've got whatever I was last doing with me, and that's what we see.
Yeah.
So when astronomers say we are seeing that early moment, that really early epoch, that's what they mean. Like the light is still carrying information about that really early moment of the universe, which is great. That's so cool.
It is, and it's mind-blowing because we can't imagine the Big Bang as being a thing that happens in a bigger universe, right? This isn't kind of, like there was a bubble of opaqueness and then it's that bubble became clear and the photons escaped into the rest of the universe. This is, remember that we're always talking about whole universe.
This is the universe.
This is
the whole thing. Yeah,
it's just that the photons are now free to move throughout that whole universe as much as they want to. They just carry on. Including
way across space and time to our telescopes where we can measure them and figure out stuff.
Yeah. It almost feels a bit sad sometimes, I think, when we do astronomy, because ultimately measurements in astronomy destroy photons, right? So sometimes I sort of feel like we just kind of ended that life of that photon, and that's been travelling since the very beginning of the universe. Aren't we mean? Is that a silly thing to think?
Yeah, no, I kind of see where you're going from there. Although there is a sense in quantum physics that built in to the photon itself, built into the very notion of the photon, is its beginning and its end. Because you can only describe in quantum physics a photon as something which is created at some interaction and destroyed at another interaction. And so at the moment that the photon left its departure point, when it was bounced off something and effectively created quantum mechanically at that point, and it then got absorbed by one of our detectors, that was always going to happen. And I think quantum mechanically, that blows my mind. But that's the way you have to think about it in quantum physics. It's crazy. Absolutely crazy.
And you don't want to open up the can of worms of fate and so on. Is that always going to happen?
No.
But anyway.
Free will, what's that?
But yeah, so we have this recombination. And I think this is the point to say this is a real turning point for the universe. Up until this point, the universe has been dominated energetically by radiation, so radiation-dominated universe. And there's been pretty much the same amount of matter and antimatter in the universe. So all particles that exist, which we call matter, have their own antiparticle. Probably the most familiar one that we have is the electron has a positron.
Positron, an anti-electron.
Yeah.
Exactly the same as far as we can tell, except positive charge instead of negative charge.
Yeah. So we have matter and antimatter. And if you put the electron and a positron together, they annihilate and you just get a bit of energy out.
Yeah. And annihilation sounds like a really violent thing. It's, from a particle physics point of view, it's really simple. The electron's here, the positron's there, they come together and they cease to exist and a photon appears. And that's all it is. And that's a very small explosion, but it's just a thing.
Yeah.
It's just what happens.
And it happens in reverse as well, right?
Yeah.
So a photon can just kind of turn into an electron and positron.
Yeah.
That's one important thing that happened in the previous 300-something thousand years that has made every bit of difference to the universe we see around us today.
Mm-hmm.
Because if you take the subtlety of the point that if you have exactly the same number of matter particles and antimatter particles existent in the universe, what's the average of those?
Well, zero.
It's not.
'Cause for every particle, there's an antiparticle. And so, so there shouldn't be anything.
Yeah.
Is what you're basically saying.
The universe shouldn't exist if you produce your matter and your antimatter in exactly the same proportions.
Right. Okay. So hang on. Let's get this straight. Every particle has an antiparticle, and there's no reason really to think of prior to this that we should have one other than the other, right? The laws of physics are sort of, as we like to say, they're symmetric that way. And so once it cools down enough, then you should have, on average, the same amount of particles and antiparticles, and they all then annihilate, and there's nothing left.
That's what we think probably should have happened.
It's not what's happened, Emily, because I can see you.
Because we all exist as matter
we're
particles.
Here, we're matter. Yeah.
So for some reason, and a reason we don't understand,
Mm-hmm.
a very, very tiny fraction more matter particles were produced in this early part of the universe than antimatter.
Right. Tiny imbalance.
Yeah, really small. Like, I can't remember the exact number, but it's 1 in the millions to billions of particles was just one extra.
Right. And like by chance?
We don't know. We don't really have a good explanation why there's more matter than antimatter.
I mean, I guess there's two possibilities there, right? Aren't there? That there's no deeper reason than, well, I mean, maybe it wasn't exactly, one tiny little margin of error there leaves you with a tiny little bit more of what we now call matter, and that's what we have left across the scale of the universe. It's not terribly much, but it's what we have. The other possibility is that there is a much more fundamental reason in that the laws of physics aren't balanced that way, that there's a tiny little difference between matter and antimatter.
Both of those are really unsettling, actually, especially for a theoretical physicist, I think, because you want things to be. Everything else in the universe seems to be very symmetric. It's very nice. It's very orderly. Our equations are nice broadly. They work. So why would there be an imbalance in one of them? That's worrying. Or you've got some kind of statistical over density of one, which is just a random chance. And then maybe if you think about that too much, that's a little bit unsettling as well.
Yeah, neither one leaves you with a lot of confidence. But from a physics point of view, it is utterly fascinating. And there's an enormous amount of work that's been going on, again, for decades, trying to really nail down, well, if the universe isn't symmetric in this way, and symmetry in a sort of really abstract way, what does that mean? And where do we find that? And how would we prove that? And there's loads of work and loads of experiments which are still hanging out there going, not sure, but we're working on it. Because it would be, huge to be able to nail that one down, to figure out why are we here?
Yeah.
Why are we here at all? We shouldn't be.
Yeah, so I think anyone going into any kind of branch of theoretical physics, these are the big things that you can dedicate your entire lives to. And I'm not convinced you're going to get these out in the next few generations of scientists necessarily, but exciting stuff to work on.
Yeah, big stuff. And I'm now thinking in terms of going back to the analogy to human children, your future child. What stage of development is this? Is this the point at which your child is now crawling around and you're looking at it going, what does it mean? How did this happen? How do you exist? How do I exist? Maybe that's it. It's the existential question of parenthood.
Yeah, or maybe it's kind of like the personality of the universe has come through.
How did you get like this? Where did that come from?
Yeah. Where does the stubbornness come from? Oh, right, yeah, the parents.
Yeah.
So, yeah, it's interesting. So we transition now from the radiation-dominated universe to the matter-dominated. We go through a period of the universe's history, which is basically going from this 380,000 years after the Big Bang, kind of up to the first million years. So, another chunk of time. We call this the Dark Ages.
Dark in the sense of not much light, dark in the sense of not a lot of learning and knowledge being produced.
Well, yeah, it's interesting because I believe that the term Dark Ages is applied to sort of medieval history is now kind of fallen out of favour.
It's a bit debunked, actually, I think, yes. Yeah.
There was a lot of really interesting stuff that people did during that period of time. However, I would argue that this is maybe what the intention was for the original Dark Ages.
Right.
Because it really is dark.
Okay. Why so dark?
Well, because you've not got anything sort of producing photons.
Oh, I see. So atoms are allowed now, and basic atoms, maybe a little bit of basic chemistry even, perhaps. But the light that we see in the universe around us comes from, like, stars.
Yeah.
And they haven't happened yet.
No, we don't have enough stuff together.
So it's literally dark.
Yeah.
Right. Other than this background glow, which is probably not very bright.
No, well, it's been already expanded so much that you're talking about photons that have been redshifted to at least the infrared.
Yeah.
So they're just kicking around. But apart from that, there's no photons being produced at all. So, and we rely on photons to see stuff.
Yeah,
right?
yeah.
That's what light is.
Yeah. Isn't it amazing to think that if the universe hadn't been able to produce stars, that would have been it?
Yeah.
That would have been it. Just this wash of atoms and cooling radiation, and then that's it. We're done. That's it for the history of the universe. But that's not what happened.
No. We're at about 100 million years after the Big Bang, then we got the first baby stars.
That, to me, seems like a story for another time.
Yes. But what was it? It's flicking on the light switch of the first few stars, and we call this reionization of the universe because we've now got a new energy source, we've got new photons, and the universe is free to develop and grow in a new phase of its life.
And the universe goes, phew, that's a relief. Phew, got away with that one. Because, that's just too depressing to think about. If that hadn't happened, was all of that, inflation and the separation of the forces and everything, for it to then just, and we're done. That's it. It's just dark now. Dark and forever expanding into the void. But then, bing, these little lights come on, bing, and the universe is now full of stars, baby stars.
Yeah, it's nice, isn't it?
Yeah.
So, maybe
fairy lights.
Our little babies are kind of up and walking and starting to be independent in the world and the universe.
And turning on light switches everywhere. That's what it's doing. Well, what an epic way to come back into producing the Syzygy podcast. It's really good to be back, and it's really good to be back, Emily, with such a big story about a big baby universe. There's a lot that has just happened in the infancy of the universe. That was exciting. But to get to that point of those early stars, bing, coming on, I think we're going to have to come back to that one. But it's not baby stars next, is it?
I think maybe we should do first stars. That would be quite a nice follow-on, wouldn't it?
Yeah, from a narrative point of view, maybe that's where we are. Okay, well, that's something to look forward to next time. Listen, Emily, it is so good to be back. And we do have a couple of ideas for shows coming up. But look, if people wanted to get in touch with us to talk to us about this episode, or indeed ideas for other episodes, or questions that you've got about what's going on in the universe around you, or indeed anything else, even if it's just to welcome us back, wish me a happy next half of a century, and wish Emily an enjoyable whatever's coming next, because it's going to be a fun ride.
Hopefully it doesn't start with a big bang.
Yeah, well, hopefully not. Emily, is there a way that people could conceivably get in touch with
Just a couple. Just a couple. So you can start on Twitter.
Yep.
So we're at SyzygyPod, SYZYGYPOD.
Yep. Take a break from all the other craziness that's happening on Twitter in the world around us and come and do some astro nerding with us, SyzygyPod. Where else can they find us?
So we're on the Instagrams.
We are.
Which I believe has to be pluralized.
Yes, the Instagrams. That's the way it works.
Yes, I thought so, yeah.
Yeah.
Facebook. You can just shove in Syzygy Podcast.
Yeah, you'll find us.
That you can Google Syzygy Podcast and it gets to us as well. Lovely website, as you say. It's fancy, new, just paid for, shiny.
Yes, it's the same old website, but it's still running, is the point.
Well, you've just kind of polished it up, and
that's an important thing. No
dust on it anymore.
No dust, and the electrons being paid for by our fabulous Patreon supporters. So that's over there at syzygy.fm. And there is a contact page there as well if you want to just send something our way.
And can I just say, I did notice you can also get merch.
That's right. We do have Syzygy merch, because that's a thing that podcasts do, right?
Yeah.
That's a thing that happens on the internet. So if you go to the website, you can go and find our merch page, and we've got Syzygy themed stuff.
Including tiny newborn baby grows.
Yes. Well, you can it's all done through a wonderful site called Redbubble, if you know it. So go and check that out, and there's all sorts of other science nerdy stuff there as well. So check out our merch page. If you want to support the show, a bunch of different ways you can do that. The biggest one is just tell everyone that you know that it exists. Tell people that there's a thing called the Syzygy Podcast and help us raise the profile and get the word out. You can leave us a review on your podcast chaser of choice. Give us some stars and a couple of words, and that helps us to rise up through the noise. Or head over to the aforementioned patreon.com and become a financial supporter of the show. For just the price of a coffee, you can help us to keep the electrons flowing and doing things in the big wide world of, who knows, maybe one day another live show. But otherwise, we should probably bring this epic episode to an end. So, Emily, I'll see you again really soon, where we continue our discussion of baby and infant things in the cosmos. What do you reckon?
Yeah, sounds brilliant.
Sounds really good. Lovely to be back. Really nice to see you, Emily. Bye, everybody. See you in a week or so.
See you later.
Bye.